So in week 3, you would have studied about, just wait a minute. So in week 3, you would have studied about principal planes. So there were 3 lectures. Lecture 7, you would have studied about principal planes and principal stress components. Okay, so and lecture 8 was about maximizing the shear component of the stress. So for finding principal planes and principal stress, we maximize the normal component of the stress. And then next lecture was about maximizing the shear component of the stress. Shear component of traction, obviously. Okay. Now lecture 9 was about Morse circle. So quickly we will recapitulate what you people have studied in these lectures, and then I'll start with some uh, problems or questions. Okay. So let me recapitulate. So no. So in lecture 7, you would have studied that normal component of traction. We have to maximize normal component of traction to get principal planes and principal stress components. So normal component of traction on an arbitrary plane is given by sigma nn, which is a normal component of stress. So it is given by a traction vector on that plane having normal vector n and dotted with that normal vector itself, right? So you know that Tn is equal to sigma times n, and that will be dotted with n. Okay, so where n is, so this is normal to the arbitrary plane, normal vector to the arbitrary plane. Obviously, it is a normal unit vector like this. Okay. Also, since it is a unit vector, the summation of all its components should be 1. So the 3 components of n also should satisfy. So I'm just writing here the 3 components of n should satisfy. So its magnitude should be 1. So this means n1 square plus n2 square, I mean sum of square of its components should be 1, right? So this should also be satisfied. Now, if you will do a constrained optimization problem, so this is kind of constrained optimization in which you have to maximize this sigma nn subjected to this constraint, right? So constraint is the magnitude of normal vector should be 1. because it's a unit vector. Okay, so this is the constraint, and you have to maximize this. So this is a constraint optimization problem. So in the lecture, sir had used Lagrange multiplier approach. So it was based on maximizing this sigma n subjected to this constraint. So this constraint is introduced using a multiplier known as Lagrange multiplier. So if you will do the Lagrange multiplier, use the Lagrange multiplier approach and perform the optimization or maximization. So you will reach to this equation, sigma n is equal to lambda n. You see that this is the eigenvalue problem. So you reach to eigenvalue problem after applying Lagrange multiplier approach or a constraint optimization approach. You do not directly reach at this point. Okay, you are maximizing the normal component of stress subjected to this constraint. So that's how you have reached at this eigenvalue problem, eigenvector problem. And you are aware now that if you solve this eigenvector problem, so eigenvalues will correspond to principal components of stress, and eigenvectors will correspond to the plane normals where the normal principal stresses are acting. Right. So I'm just writing few notes. So note one is stress at a point have their normals equal to eigenvectors of the stress tensor. Whereas the principal components are given by the eigenvalues of the stress tensor. So here actually I should write principal stress at a point. So yeah. So principal stress at a point have their normal equal to eigenvectors because they are acting on a plane which have normal equal to eigenvectors. Whereas the principal components, the magnitude of the principal stresses, or yeah. So the components of the principal stresses, not the magnitude, components of the principal stresses are given by eigenvalue of the stress tensor. So they can be tensile and compressive both. So second point is so at a point, so you know that this sigma is a 3 cross 3 symmetric matrix, and this n is a normal vector. It also has three components. So this problem will have at most three eigenvalues, three different eigenvalues, and corresponding to each eigenvalue, there will be eigenvector, right? So at most, there are three eigenvectors and three eigenvalues, right? So we can say that there can be at most three principal planes at a point. So principal plane at a point are three in number. And also they are perpendicular to each other. Right? The third note is So any stress matrix in any coordinate system can always be transformed to principal coordinate system. So you can always transform. Let's say you have a coordinate system E1, E2, E3, and stress tensor has been expressed in that coordinate system. So you can always transform stresses such that you can go to the principal coordinate system, and in principal coordinate system only the diagonal elements will be non-zero and non-diagonal elements will be zero. So here we can write any stress matrix in any coordinate system can always transform to become diagonal in the coordinate system. So diagonal in the coordinate system whose basis vectors are along the eigenvectors of the stress matrix of the stress tensor, you can say. So from any coordinate system, you can go to principal coordinate system, or a coordinate system in which the stress matrix has only non-zero diagonal elements, and the basis of that coordinate system will be along the eigenvectors of the stress tensor. So, for example, if we transform a stress tensor into a coordinate system which is aligned along the eigenvectors, so it will have only three non-zero components. So lambda 1 0 0 0, lambda 2 0 0 0 lambda 3. Right, so lambda 1, lambda 2, lambda 3 are three eigenvalues of the stress tensor in the coordinate system which is aligned along the eigenvectors of the stress tensor matrix. Okay, and you in this formula I have already written, you know that sigma n, that is normal component of stress, is given by normal component of stress on a plane having normal n vector, that will be given by traction on that traction vector on that plane. So this is a traction vector on a plane having normal vector as n vector dotted with that n vector, right? So this will be normal component of the strain. And now how the shear component of the strain will be given. So you know that, let's say this is a plane. Okay, so and on this plane, let's say you have this as normal vector and the traction vector is going like this. Let's say this is traction vector. Now the normal component is you have taken the component of this traction vector along this normal direction. The shear component will be let's say in this direction, right? Which is along the plane. So we will only calculate the magnitude of shear component. So let's say this is a shear component tau. This already you would have studied in the lectures. I'm just recapitulating. So since this tau n and tn, so n and tau are perpendicular to each other and tn is the resultant vector. So we can write that magnitude of tn, we can apply the Pythagoras theorem. So we can say that the magnitude of tn to the whole square is, will be equal to tau square plus sigma n square, right? So we can say that sigma, also this is equal to sigma times n. So tau square can be written as t and a magnitude of the traction vector squared minus sigma n squared, right? So the traction vector can be written as, this is sigma n. Okay. So traction vector can be written as sigma n, and we'll take magnitude of that n square minus sigma n can be written as 2 n sigma n dot n. So finally, we will get this as the magnitude of the shear stress on a plane having normal vector as n vector. So if we try to write this in terms of principal planes, okay, let's say you have three, let's say now the stresses are available in the principal coordinate system. So, and you have a plane which is aligned, which is having its component as n1, n2, n3 with respect to the principal plane. Okay. Then you can expand this tau and the expression will be simple because now this sigma will have only non-zero diagonal elements and all the off-diagonal elements will be zero. So if you do that, so it will be tau square that will be equal to, let me just write one more thing. So shear component fraction in terms of principal planes. Right? We do that. So let's just write. So tau square will be equal to sigma. Sigma will be nothing but a matrix, 3 cross 3 matrix, and let's say it is lambda 1 0 0 0 lambda 2 0 and 0 0 lambda 3. Right? And n will be given by, this is the vector n1, n2, n3. So components of n are n1, n2, n3. And obviously matrix multiplied by a vector will be a vector, and you have to take magnitude of this vector and square that minus sigma n. So you know that if sigma n will be this multiplied with n, so that will be lambda 1 n1, and lambda 2 n2, and lambda 3 n3. So three components will be lambda 1 n1, lambda 2 n2, and lambda 3 n3. And if you again dot with n, so you'll get lambda 1 n1 square plus lambda 2 n2 square plus lambda 3 n3 square. So I'm just writing it directly. So you will get lambda 1 n1 square plus lambda 2 n2 square plus lambda 3 n3 square. Right? So finally, if you find this also, so here also this vector will have the components lambda 1 and n1, lambda 2 and 2, lambda 3 and 3. If you take magnitude of that, will be lambda 1 n1 square, lambda 1 square n1 square plus lambda 2 square n2 square, and lambda plus lambda 3 square n3 square, and square root will get cancelled with this square. So you will get finally lambda 1 square n1 square plus lambda 2 square n2 square plus lambda 3 square n3 square minus this expression, which is lambda 1 n1 square plus lambda 2 n2 square plus lambda 3 n3 square. So this you have got your square of stress, shear stress, that is equal to that you have expressed in terms of the principal values of the strain components, the principal value of the strain tensor, and the these normal vectors. So these normal vectors, I mean this normal vector is with respect to your principal directions. Okay. You will measure your normal vector. So you consider your basis vector as your principal directions, and considering that as basis vectors, you will now um, measure your normal vector. So then there were few more results in this writing. So magnitude of traction component on a plane having maximum shear. So you know that magnitude of shear component having, I mean magnitude of shear component on a plane having maximum normal component of the traction. So on that plane shear will be zero, of course, on principal. So those are known as principal planes. Principal planes shear components are zero, but it's not the same story with the planes having maximum shear stress. So the planes having maximum shear stress, there you will have some value of the normal stress as well. So magnitude of traction components on plane having maximum shear. There will be some value. So maximum shear will have this value. Maximum shear will have the value of lambda 1 minus lambda 2 by 2. So let's say this is the plane which is perpendicular. So this is a plane whose normal vector is perpendicular to the third principal direction. So there you will have two principal stresses, sigma 1 and lambda 1 and lambda 2, and maximum shear will be given by uh, maximum shear in that plane. So that will be given by this one. So it will be lambda 1, first principal stress minus second principal stress divided by 2. So similarly, if you want to find maximum shear stress on a plane which is perpendicular to, so let's say you want to find maximum shear on a plane whose normal vector is perpendicular to the first principal direction. So now you will have, so since you are perpendicular to, so since your plane has a normal vector perpendicular to first principal direction, so it will have only, I mean, so shear components will depend on lambda 2 and lambda 3 because your plane normal is perpendicular to the first principal direction. So now you will have lambda 2 minus lambda 3 divided by 2. Similarly, if you want to find out maximum shear on a plane with plane normal perpendicular to the second principal direction, so now you will have only lambda 1 and lambda 3. So your shear stress will be given by lambda 1 minus lambda 3 by 2. Okay. So this is how you calculate maximum shear stress on three different planes. So this is a plane having plane normal. So this is plane normal perpendicular to third principal direction. Principal direction. Similarly, this has a plane normal perpendicular to first principal direction. Similarly, this has a plane normal perpendicular to second principal direction. Right? So, so when you are perpendicular to first principal direction, so let's say your plane normal is perpendicular to third principal direction. So now you are moving in um, the principal direction and moving in the plane with principal direction with the first and second principal direction, right? So you are not going in third principal direction. So let's say, you would have studied all these in the lecture. I'm just recapitulating. So now you will not go, your plane normal. So let's say this is the third principal direction. And this is the plane, this in which this white pen is moving. So this plane contains first and second principal direction. So now you are moving in only first and second principal directions. So that the plane on which you want to find out your maximum shear stress, so that plane will always be perpendicular to this. The plane normal. So plane normal will be this in this right direction only. So plane normal will be perpendicular to this third direction. Right? So in this plane you want to find out your shear stress. So okay. Similarly, you can interpret the second and third case as well. Now let's come on to Mohr circle. Mohr circle is a graphical representation of the, I mean, through Mohr circle, you can just have a graphical representation of principal planes and principal stresses and maximum shear stress, and at what angle maximum shear stress is aligned to the principal planes. All this information you can get through graphical representation. So, so there is a condition to use more circles. So the condition to use more circle is that. So what is the condition? Can you tell me? You would have studied in the lectures. The condition is that your plane normal, in which your plane normal should be perpendicular to one of the principal directions, right? So the plane on which you want to plot the stresses or get the normal and shear components. So that plane should be perpendicular to one of the principal planes. That is the only condition. The condition to use more circle is that the plane normal has to be perpendicular to one of the principal planes. Principal stress directions. So let's say you have a stress like this and you want to take a coordinate system. Let's say take a coordinate system such that your plane normals, whatever plane you take it, your plane normals are always perpendicular to the third principal stress or third principal direction, right? So then you have, then your these components will be zero because this third column, you know that it represents a traction vector on a plane having normal vector as E3, right? So there actually, since you're taking, since your third plane is your third principal plane, right? So since you're taking a plane which is perpendicular to the third principal direction, so your third direction here will be principal direction. So now your shear components will be zero. So this, so for this traction, shear components will be this one, and there will be only normal component. So here this value will be non-zero, and due to symmetry, these values will also be zero. So this is a stress tensor. So this can be a stress tensor on planes having plane normal perpendicular to the third principal direction. So, so this is obviously lambda 3. This is the third principal, third eigenvalue, which is the maximum value of the normal. I mean, it is third principal direction, so that's why this is the value of the normal stress on that principal plane. Okay. You can ask me if you have any questions in this. So I'm going to write formula of normal and shear stress in terms of, so let's say you have studied this actually already. So let's say you have this plane, and let's say this is x and this is y. And so this is sigma xs. Here you will have sigma xy, sigma yy into xy. All three will be present. And let's say there is a plane here, and its plane normal is, let's say, like this. Right? So let's say this is the plane normal, and on this plane you want to find out the normal and shear stress. And let's say this plane is making an angle of alpha with x-axis. So in that case, your normal and shear stresses will be given by sigma xx sigma 2 plus sigma xx minus sigma yy by 2 times cos 2 alpha plus 2xy sin 2 alpha, right? And your shear components will be given by, I mean, shear stress will be given by minus of sigma xx minus sigma yy by 2 sin 2 alpha plus 2xy plus 2 alpha. Okay. So this you would have studied. So there is a complete derivation in the lectures. You can go to the NPTEL lectures by Professor Ajeet Kumar, who is taking this course, and then you can see the derivation. So just quickly recapitulating. So let's draw more circle based on this. So from these equations, you can derive the equation of a circle. So if you do that, so you will get a more circle. Just drawing that. So that more circle is, let's start. So center of the circle will be sigma xx plus sigma yy by 2. Let's say this is the center of your circle, and let's say you have some radius. This is your radius, and this point here. So that will be sigma xx, and this height will be tau xy. So this point will be sigma xx times tau xy. And somewhere here you have sigma yy also. Let's say here you have sigma yy. Okay, and if you take this as radius and draw a circle, so you will get something like this. Okay, you will get something like this. So this is your more circle. So you're taking this as a radius, and the value of this radius will be how much? You can just apply Pythagoras theorem. So value of this radius will be, so this distance plus this distance. So this distance will be sigma xx minus sigma yy by 2, and this distance will be 2xy. So this will be sigma, if you apply Pythagoras theorem, so it will be sigma xx minus sigma yy by 2 to the whole square plus 2xy to the whole square. We get this radius, and this angle is given by 2 phi. Obviously, this is the plane that you are at. So your sigma xx, so this direction is represented by this line here. And this is your principal plane because, so this axis is the shear axis. I mean, on this axis we are plotting the shear stress, and on this axis we are plotting the normal stress. So here, if you see these points, so these points, so this will correspond to lambda 1 and this will correspond to lambda 2. Because you see, at this point your shear stress is 0, so this will be principal plane. And this also will be principal plane, and this will be the value of the principal stresses. Here only you have normal stress. So this plane is inclined at an angle of, I mean, this is not exact that angle, but half of this angle will be angle between the x-axis and the principal plane. So there, angle phi is the angle between your x-axis, and somewhere some principal plane will be there, which will be inclined at angle phi with the x-axis. Okay. So, and you can also write radius in terms of lambda 1 and lambda 2. So if you do that, so you know that this is the center, and this is lambda 1, this is lambda 2. So radius will be lambda 1 minus lambda 2 by 2. This value minus this value will give you this length, and divide by 2 will give you radius. Okay. So lambda 2, you can also write in terms of sigma xx plus sigma y by 2, which is center, right? And from the center, if you, this is the center, and if you subtract radius from it, you will get lambda 2, and lambda 1 will be center plus radius. And radius you already have in terms of sigma xx and sigma y. This is all about the recapitulation of the lectures. Now let's start with some questions. You can ask me if you have any questions from the lectures. Okay. So let me give some questions to you. Let's start with questions. So this is question one. Let me write it. Then we will think how to do it. I'll start with simple problems. So the state of stress at a point in a body is given by, that is given by sigma, which is the second order tensor. So this will be represented as a matrix. So this is given by 1, 2, 3, and 2, 4, 5, and 3, 5, 0. And these components are in megapascal. Okay. So whatever the coordinate system will be, it will be. So let's say it's E1, E2, E3 coordinate system. So this is the attraction vector on a, I mean, this 1, 2, 3 represents component of the attraction vector on a plane having plane normal E1. This is the component of traction vector on a plane having plane normal E2, and these are the components of the traction vector on a plane having plane normal E3. So the question is, we have to find what is the normal stress on each of the coordinate planes. So coordinate planes have, let's say, with normal in E1, E2, E3 directions. Okay. So how will you find what is the normal stress on each of the coordinate planes? How will you find that? So you see here, I told you that this first column represents the traction vector on a plane having plane normal E1. So out of that, this is the normal component on that plane, and these two are shear components. So on a plane having plane normal E1, the normal component of the traction will be 1, right? So it is right. The normal stress on E1 plane is how much? This is 1 megapascal. Now, similarly, can you tell me the normal stress on E2 plane? How much that will be? Yeah, someone, would anyone like to volunteer in answering? Yes, Rishabh. Okay, so you know that the second column represents the attraction vector on a plane with plane normal E2. So this is the traction vector. So this these two will be shear components, and diagonal element will be the normal component. So the value of the normal component will be 4 megapascal. Similarly, the normal stress on E3 plane, that will be 0, because in the third column the diagonal component is 0. So that's a normal component on E3 plane will be 0. Okay, let's go to the next part. If you have any doubt, you can stop me. So let's go to the next part. So next part says, said what it says, what is the total shearing stress or shear stress on each of the coordinate planes. Obviously, these coordinate planes have directions as E1, E2, E3. So now you have to find what is the total shearing stress on each of the coordinate planes. So you know that this first column represents traction vector on plane normal, traction vector on a plane with plane normal E1. So on that plane, these two are shear components, but we want total shearing stress. So we'll have to take the resultant of these two shear components. So that will be square root of 2 square plus 3 square. So we can say that total shearing stress on even plane is, so 2 square plus 3 square, because these are the shear components. That will be root 30 megapascal. Now you have to find total shearing stress on into plane. So that will be, so this is the traction vector on a plane normal, on a plane with plane normal E2. So the off diagonal terms will be shear components. So those are 2 and 5. So total shearing stress will be 2 square plus 5 square. So that will be 29, root of 29. Right. And similarly, you have total shearing stress on E3 plane. So that will be given by, obviously off diagonal terms are 3 and 5 here in the third column. That will be 3 square plus 5 square. So that will be under root of 34. Right. So coming on to the next problem. Do you have any doubt in this problem? So I think it was a bit simple. If you understand the stress tensor and what is the significance of each of the elements or each of the column of stress tensor, then you can do it. Okay. So coming on to question number 2. You have to, so it's, let me just camera. Yeah. In question number 2, it is given that the state of stress at a point in a body is given by, so again you have the state of stress given to you, sigma. So that is denoted as 2 minus 1 3 and minus 1 4 0 and 3 0 minus 1, and that is again in megapascal. So this is the state of stress that is given to you. Now you have to find traction vector at a point on the plane whose normal is in the direction of 2E1 plus 2E2 plus E3. So to find the traction vector on a plane whose normal is in this direction. Okay. So firstly, we'll have to make this normal vector unity, because we need unit normal vector to find out the traction. So what we can do is, for solution purpose, what you can do is you can make this as unity. So your unit normal vector will be given by 2e1 plus 2e2 plus e3 divided by 2 square plus 2 square plus 1. That will be square root of 9, which is 3. So there is 1 by 3. So now once you have the traction vector, you can easily calculate. And once you have this normal vector, you can easily calculate traction vector. So you know that traction vector on a plane with plane normal n is given by sigma times n. Okay. So sigma you already have. So just 2 minus 1, 3, minus 1, 4, 0. And this n is 1 by 3 I'm writing here, and the rest of the n you can write here. So this is 2, 2, and 1. Okay. So if you solve this, first if you solve this, 2 multiplied by 2 will be 4 minus 2. So that will be 2 plus 3. So that will be 7. Sorry, 5. So we get 5. So 1 by 3 will remain as it is. I'm keeping this 1 by 3 as it is. So first component will be 5. So, and second component will be minus 1 so minus 2 and plus 8. So you will get 6. And third one will be, we get 3 times 2 will be 6 and minus 1. So you will get 5 again. This is your fraction vector on a plane with normal as this vector. Okay. So now going to the second part of this question. So the second part says you have to determine the magnitude of normal and shearing stress on this plane. You have to determine the magnitude of the normal and shearing strain. Sorry, shearing stress. We're not dealing with strain right now. So yeah, how will you do it? Now you have traction vector on this plane. So to get the normal, so I've already told you that since let's say this is the plane, and this has this normal vector n, and this has this traction vector Tn. So to get the normal component of the traction vector, that is the magnitude of the normal stress, you just find the component of traction vector along this normal vector. So that is nothing but T dot n. So sigma and n you already know that is given by Tn dot n. Right? If you do dot product, so you will get, so how much value you will get. So 1 by 3 and 1 by 3 will be 1 by 9, and this will be 5 to the 10, 6 to the 18, so 28 plus 5. So that will be 33. So we get 33 by 9. So I think we get the 33. So 5 to the 10, 6 to the 12. Okay. 22 plus 5. You get 27, not 33. So finally you will get 27 by 9. Which is 6. Right. Okay, so this was sigma. So this is sigma nn, which is in MPa, megapascal. Now, how you find this shear stress components? Let's say this is the shear stress, resultant shear stress. Okay, so to find shear stress, you know that you have to apply Pythagoras theorem. So shear stress will be magnitude of the traction vector square minus, and here actually this is the normal vector, but here you have sigma and elements. Okay, so here you just minus sigma and square, right? So if you do that, so you get traction vector. I mean, the shear stress. Shear stress will be square root of magnitude of this traction vector. So magnitude will be given by this is 1 by 9, 25 plus 36 plus 25. 25, 25 will be 50 plus 36 will be 86. 86 by 9. So this is 86 by 9 minus 9. So what you will get? So you'll get 5 by 9, square root of 5 by 9. So which if you calculate, so it will come out to be 0.745. You can just do it. So it will be root 5 by 3, which will come out to be 0.745. Okay. Okay, so is there any questions or doubts in this problem? If there are no doubts, let me go to the next question. So question 3. It says that let's say you have a plane passing through a point. So let's say you have a plane which is passing through the point at which stress tensor is defined in the previous question, in this question. So a plane is passing through this point, and the plane is also parallel to, and the plane is parallel to. The plane is parallel to another plane, and the equation of that plane is given by x1 minus 2x2 plus 3x3 is equal to 4. So that is a plane, that is another plane. So this plane is parallel to this plane. Okay. So you have to find out what is the value of the normal stress on this plane, the plane. So how do we solve this thing? So since a plane is passed, so there was a point at which stress tensor has been defined. Now you have a plane which is passing through that point, and the plane is parallel to another plane. Okay. So since both of these planes are parallel, their normals will also be parallel, right? So if we find the normal of this plane, so which should be something in this direction, let's say. If we find the normal of this plane, we can get the normal of this plane also. So I'll find the normal of a plane. So let's say you have a plane here, and this is, let's say, your coordinate axis. So x2, x, and this plane is there in some space. So let's say you have a point here, x, which is denoted by x, and another point here, which is which is denoted by x plus dx. So x and x plus dx are position vectors. So this small incremental vector which is lying in the plane, in this plane, will be given by dx, right? So this vector is given by dx. Okay. So let's say that this position vector has component x1, x2, x3. So this, since this position vector is lying on this plane, it will satisfy the equation of the plane, and this position vector will also satisfy the equation of the plane. What I mean to say is, if I satisfy this position vector, the equation of this plane, so it will be x1 minus 2x2 plus 3x3 will be equal to 4. And this second position vector will also satisfy the equation of the plane. So that will be x1 plus dx1. That will be the first x component. I mean, x component of the position vector minus 2x2. At the place of x2, I have x2 plus dx2 because that is a y component of the position vector minus and plus 3 times x3 plus dx3. So both of these points are lying on the plane, so that's why they will satisfy the equation of the plane. So now if you subtract these two equations, so if you subtract first equation from the second equation, you will get dx1 minus 2 dx2 plus 3 dx3 equal to 0, right? And if I write this in terms of dot product, so it will be um, dot product of these two vectors, dx1, dx2, dx3. Let's say this is the vector, only vector, and I take transpose of this dotted with this vector 1 minus 2 3, right? If we do dot product, so dot product of these two vectors are 0. So since dot product of these two vectors are 0, so they should be perpendicular to each other. So this vector dx1, dx2, dx3, so this is nothing but this dx vector. So this dx vector is lying in this plane. So that's why the second vector has to be perpendicular to this plane. So we have got this normal vector, which is perpendicular to this plane, which you could also find from this coefficient of the plane, coefficient of the equation of the plane. So 1 minus 2, 3. So this will be three components of this vector. But this was a kind of proof why the coefficients are equal to normal vector. Okay, so now your normal vector. So obviously I have to take unit normal vector. So that will be e1 minus 2e2 plus e3, 3e3. And I take unit vector. So that will be 1 plus 4 plus 9. That will be square root of 14, right? So now you will have 1 over square root of 14 times e1 vector minus 2 into e2 vector plus 3 into e3 vector. Okay. So how you find, so what you need to find out is you have to find the value of the normal stress on the plane. So value of the normal stress is given by, firstly, so that will be, let's say you find the traction. So traction will be given by sigma times n, and you want to find the normal, you want to find the component of this traction along the normal direction. So that will be t dot n, which is known as sigma nn. So that will be nothing but sigma n dot n, right? So let's find out firstly t dot n. Then I mean, firstly we can find traction vector. So that will be sigma times n. So we get 1 over square root of 14. Sigma is given as, sigma is previous one only. So that is 2 minus 1 3 minus 1 4 0 3 into minus 1. So right, and this 1 over 14 is coming from this normal vector actually, and so rest of the components will be here 1 minus 2 and 3. Right. So if you solve this, finally you can try to solve this. So 1 over square root of 14. So if you multiply, so this will be 2 times 1 will be 2 minus 1 times minus 2 will be 2, so that will be 4, and 3 plus 3 will be 9. So 9 plus 4 will be 13. So this first component will be 13. Then you can try this, then minus 1 minus 8, so that will be minus 9, right? And last one will be 3 and minus 3, so that will be 0. Here we have got this as traction vector. So now the normal component, you know, sigma nn, so that is given by traction vector dotted with this n vector. So this traction vector, which is 13 minus 9 0. If you dot with n vector, which was again 1 over root 14 and 1 minus 2 3. You do that, so you will get 1 over 14, and then 13 times 1 will be 13, and 9 times 2 will be 18, and this will be 0. So, so that will be 31. Yeah. So 13 plus 11. So you get 31 by 14. So if you solve this, you will get 2.21. Okay. So this is the answer. So the only challenge you can say in this question was to find out this plane normal. You should either you can derive using this method, or putting this, if you have information, if you know that coefficient of the equation of the plane gives the plane normal vector. So that also you can use. Okay. Now going to the next question, which is question number 4. So this says that, let's say you have given that sigma 11 is equal to 1 megapascal, and sigma 22 is equal to minus 1 megapascal, and all other stress components are 0 at a particular point. So you have to prove that only plane on which the traction vector is 0 is the plane with normal in E3 direction. You have to prove this. So it is given to you that given that sigma 1 is equal to 1 megapascal, sigma 22 is minus 1 megapascal, and all other sigma ij are 0 at a point. You have to prove that only plane on which traction vector is 0 is a plane with normal in E3 direction. So let's construct the stress tensor. So stress tensor will be given by 1 0 0, 0 minus 1 0, and 0 0 0, right? Because sigma 1 1 and sigma 2 2 have some values, other components are 0. And from this stress tensor only you can tell that, so because first column tells us about traction vector in even direction. I mean traction vector on a plane with plane normal even. Second column tells us that it tells us about the components of traction vector on a plane with plane normal E2. And the third column tells us about traction vector on a plane with plane normal E3. So you see here that traction vector on a plane on plane normal E3 is 0. That proves this point, that only plane on which traction vector is 0 is the plane with normal in E3 direction. Okay. But we can prove also, let's say we have some traction vector and we want to find this traction vector on some plane with plane normal n. Okay, so this is 1 0 0 0 minus 1 0. So let's say that plane. So we want to find traction vector on a plane with plane normal n, and that plane normal has components n1 and 12. N3 along the direction C1 equal to 3. So finally, what you will get N1 minus N2. I mean, if you do multiplication, you will get 0 here. So from this, what you can say is, let's say you want to find out traction vector on a plane normal, on a plane with plane normal even. So in case of plane normal even, you will have N1 as 1, N2 as 0, and 3 as 0. So you'll have components as 1, 0, 0. When your plane normal is E2, you're only I mean this vector, if you see here, this vector will be 0, 1, 0. So your components will be, so only N2 is non-zero, so your components will be 0, minus 1, 0. And on a plane with plane normal E3, so your components will be 0, 0, 1. So this will be 0, 0, 1, which will lead to, so N1 is also 0, N2 is also 0, and N3 doesn't matter whatever the value of, when it doesn't matter what is the value of N3. For all the values of N3, it's going to be 0. So all three will be 0 in case of, in case your plane is having a plane normal E3. Okay. So thus we have proved that only plane on which the traction vector is 0 is the plane with plane normal in E3 direction. Okay. Your traction vector is given by N1 even minus N2. From here you can see this is first direction and this is the third direction. So let's go to the next question. Question number 5 says, let's suppose, this is a good question. Let's suppose Tm and Tn be traction values on planes defined by the unit vectors m and n, m and n respectively. Okay. And let's say these traction vectors are defined on a point, so that point pass through, I mean they pass through the point P. So what you have to prove? So you have to prove that if K is a unit vector, that determines a plane that contains Tm and Tn. Then you have to prove that then 2K is perpendicular to M and N. I'll explain straight. So it's been given here that suppose Tm and Tn retraction values on planes defined by M and N vectors. So you have to prove that if K is a unit vector, that determines a plane that contains Tm and Tn. So let's say this is Tm and this is Tn. So a plane can be made to pass through these two vectors, right? So if you have two vectors, a plane can pass through both of them. So and K is a unit vector, which determines this plane means the K will be the normal vector to this plane, right? Because the normal vector of a plane determines that plane. K will be normal vector to this plane. So normal to this plane can be, how can we find it? So if we take the cross product of these two vectors, Tm and Tn, we can get a normal direction. And we have taken unit normal vectors, we'll take magnitude of that as well. So let's just do that. So K is a unit vector which is perpendicular to Tm and which is perpendicular to the plane. Is a normal vector to the plane containing Tm and Tn. So this will be Tm cross Tn. And that is Tm. I mean, we'll divide it by the magnitude also. Okay. So this will be K vector. So let's say this is one. And we have to prove that K is perpendicular to M and N, right? So obviously K is perpendicular to Tm and Tn. But we have to prove that this K is perpendicular to M and N also. So we know that so Tk will be given by sigma times K vector, right? Traction on this plane with plane normal K will be given by sigma times K, and traction on plane with normal vector as M vector will be given by sigma times M. The stress tensor at a point will have fixed values. So I mean in a particular coordinate system. And En will be given by sigma times N, right? We have these values. Now we want to prove that this Tk is perpendicular to M and N. So we have to take dot product of Tk with M and N, right? So if we take M dot Tk, let's see what happens. So Tk is traction vector on a plane with plane normal as K vector. So if you substitute K, so that Tk, so that will be sigma times K vector, right? So and you must be aware that if I apply this property here, let's say you have A vector times this matrix A times this B vector. So A is dotted with this. So this can be written as A transpose times A vector dotted with B vector. So this is something, the definition of transpose of second order tensor. So using this property, I can do like this: sigma transpose M dot K, right? So sigma transpose, again, sigma is a symmetric matrix. So sigma transpose will be equal to sigma. This will be sigma times M dot K. Sigma times M is nothing but Tm, right? So this is Tm dot K. Okay, so You can now substitute the value of k here. K was, so if I substitute the value of k, so Tm dot k is Tm cross Tn over Tm cross Tn, right? So if you see carefully, this is nothing but scalar triplet product. So how do you find scalar triplet product? You just take these three vectors as three rows of a matrix and find it, determine it. Now, since these two vectors are same, the two rows of the matrix will be same. So that's why the determinant will be zero, because it will be a system of, I mean, two rows will be linearly dependent. So that's why determinant will be zero. So this will lead to zero value. So we have proved that if we do dot product of m vector and attraction vector on a plane with plane normal ek, that is zero. It means attraction vector on a plane normal, so attraction vector on a plane with plane normal ek is perpendicular to m, right? So that's why we have proved that tk is, and this was the first point I think we had to prove tk is perpendicular to m. Similarly, you can prove tk is perpendicular to n as well. So you don't have to do anything, you just do tk dot n. If you do, so let's say you do tk dot n, again tk can be written as sigma times k dot n. So sigma can go there, so that will be k dot sigma transpose n. Sigma transpose is sigma again, because this is symmetric, sigma times n. So if you will do that, it will be k dot sigma times n will be nothing but tn, right? So if we now substitute the value of k, so that is tm cross tn over magnitude of tm cross tn dot with of here, let's say tn. It's consistently right. Okay, so this will also be zero, because again it is a scalar triplet product and two rows are same, so this will lead to zero. So this implies that a is perpendicular to zero. A is actually not. A is perpendicular to Tn also. That's why we have proved that K is perpendicular to both Tm and Tn. So let's go to question number 6. It says that it is true or false. You just have to say true or false. Okay. The question is, on the plane of maximum shearing stress, the normal stress is always zero. This is the question. So can you tell me whether this is true or false? Yes, anybody? So we can draw more circle for this to get the solution of this. You can draw more circles. So it's not always zero. Sometimes it can become zero. Actually, let's say a more circle is like this. Okay. Let's say a more circle is like this. So here you see that the maximum shearing stress is this one, because here you have shear stress. Here you have normal stress. And maximum shearing stress is this one. So here maximum shearing stress At this point, your this normal stress is not zero. Here you have some value of normal stress, right? So let's say this is tau max, and let's say here you have sigma one, let's say sort of principle. So sigma naught, you can see. So this point will be, so here your normal stress is not zero. Sometimes, but it can be zero also if you have this kind of Mohr circle, let's say. In this kind of Mohr circle, actually maximum shear stress is lying here at this point. Let's say it's lying at this point. So here the normal stress will be zero because it is at the origin. But it's not always the case. So that's why this statement is false. That's why the statement is false. Yes. So on to the next question. So you have been given that stress matrix that is denoted by sigma, that will be given by 0, 100, 0, and 100, 0, 0, and 0, 0, 0. Okay. So let's say you have the stress matrix. Now you have to find the maximum and minimum normal stresses and the planes on which they act. Also, you have to find the maximum shearing stress and the plane on which it acts. So you know that to find the maximum and minimum normal stresses and the planes on which they act, you have to do eigenvalue analysis. So eigenvalues will be your values of the normal stresses and eigenvectors will be corresponding normal vectors to the planes on which the principal stresses are acting. So let's do the solution. Let's first do, and then it's part one, part two. Let's solve for first part. So if you do eigenvalue analysis, so there is nothing but sigma x is equal to lambda x. If you do that, so you get sigma minus lambda I, and that times x should be 0. So to get non-trivial solution, non-trivial means one solution will be obviously x will be 0, 0, 0. That doesn't make any sense. Your eigenvector are 0, 0, 0. So this is a point vector. So to get non-trivial solution means apart from the 0, 0, 0 solution. So since this on the right hand side you don't have anything, so this is a homogeneous system of linear equations. So to get non-trivial solution, your either of the two rows should be linearly dependent. So if your out of three equations, two equations are dependent on each other, so you can actually effectively you have only two independent equations. Once you have two independent equations, you can express uh, your solution. You can have many solutions, right? But those solutions won't be 0, 0, 0. Those solutions will not be trivial solutions. Okay. So basically we want non-trivial solution. For that, we will have to make our system of equations, two equations that is linearly dependent and independent on each other. It means the determinant now, because the two rows now will be similar or dependent on each other. So determinant will be zero. So determinant, that's where this lambda minus sigma minus lambda I should be zero. So I'm just explaining the basic things. Okay. If you do that, now you will get so 0 minus lambda 100 0. So let me put the determinant sign. I is nothing but identity matrix. So yes, so this determinant should be equal to 0. If you solve this, you will get cubic equation. So that will be lambda times lambda square minus 100 square. That should be equal to 0. So there are, so obviously lambda is equal to 0 is not a solution because that's a trivial solution. We won't take lambda equal to 0. Um, sorry, I think trivial solutions we have already avoided actually, yeah, by putting determinant equal to 0. So it has three solutions, obviously. So one is lambda 1 is equal to 100, second one is lambda 2 is equal to minus 100, and third one is lambda 3 is equal to 0. Okay, so we have three solutions. So we have to find the maximum and minimum normal stresses. Obviously, maximum principal stress will be this, minimum principal stress will be this. If you try to draw a more circle here, let's say this is sigma, this is tau principal stresses are this. So this is 100, and then since it's minus 100, so a circle will pass. Oh, yeah. So let me adjust these points according to the circle. Okay, so you are getting this circle. The center will be at 0, 0, and its maximum shear stress will also be 100. This angle is obviously 90 degrees. So, okay. Anyway, so we have found that maximum normal stress is 100 and minimum normal stress is minus 100. And right, and we have to now find the direction. So we have to find the planes on which these normal stresses are acting, right? So for that, we have to find eigenvectors. So if you find eigenvectors, so you have to do sigma, sorry, sigma x is equal to lambda x. Let's take first eigenvalue, which is lambda is equal to 100. So sigma, again, you know that it is 0, 100, 0, 100, 0, 0, and the rest of the things are 0. Okay. X is, let's say, x1, x2, x3, and lambda is 100, so 100 times. This is corresponding to maximum normal stress. So you want to find eigenvector corresponding to the maximum principal value. So if you solve this, we'll get 100x2, that is 100, that is equal to 100x1. And again here also 100x2, sorry, 100x1 actually here. 100x1, that should be equal to 100x2. And so obviously x3 will be 0. So this will be 0 is equal to 100x3. So x3 is 0 obviously, and you are getting relation from these two, you are getting a relationship that both these are dependent on each other. So x1 will be equal to x2, right? So now we try to write the eigenvector. So it can be, let's say x, we take x1, x2 as 1, 1. And we normalize it. So we get eigenvector as, so let's say we denote it with n. So this is 1, 1, and 0. And if we take unit terminal vector, it will be 1 by root. So that can be written as 1 by root 2. So even proceed, right? Because along x direction, it has value 1, along y direction, so it has value 1. So this is the direction of, this is the normal vector, I mean, which is normal to the plane with maximum principal value of the normal stress and maximum value of the normal stress. This is maximum principal direction. And similarly, we can find the eigenvector corresponding to this minimum value of the normal stress. If we do that, so we will finally, this equation will hold, but here only 100 will be replaced by minus 100. So in that case, we'll get 100x2 is equal to minus 100x1, and 100x1 will be equal to minus 100x2. Let's put this as n1. So n0 obviously will be minus 100x. From these two equations, you will get x1 is equal to minus x2. Instead of now 1, 1, we have minus 1 1. So this will remain same, or you can say 1 minus 1 0. So now you will have e2 as e1 minus e2, right? Okay. So so in this way, you have found out the direction, the maximum and minimum normal stresses, and the direction of the principal planes. Now, in the second part, you have to find maximum shearing stress and the plane on which it acts. Firstly, find the maximum shearing stress. So from Mohr circle, it's obvious that it is equal to 100 here. And the plane on which it acts, so we have to express this in terms of E1, E2, E3. So because let's say this sigma will be in some coordinate system. So let's say that coordinate system will be here. This line denotes that coordinate system. And this angle is 2 phi. So we have we have just found out that these normal vectors are like this. Okay, so maximum shearing stress, we can use the formula also, or we know that tau max is given by lambda 1 minus lambda 2 by 2, and magnitude of that. Lambda 1 is 100 and lambda 2 is minus 100. So we will get 100, right? And the plane on which it acts, so that was that is given by, you can see the lectures for this formula. So that is given by n1 plus minus n2 divided by 2. So if you do n1 plus n2, so here you will get n1 plus n2, so e2 and e2 will get cancelled. And so actually it is divided by root 2 mod 2. So N2 and E, I mean this E2 and E2 will get cancelled, and you will get 2 root 2 by root 2, and here also there is root 2. So you will be left with E1. First direction is this. And when you do N1 minus N2, so if you do that, so you get 2 E2 by root 2 and 1 root 2 again in the denominator, so you get E2. So on E1 and E2 planes, your maximum sharing stress will be there. And that is very obvious from the Mohr circle also, because if you see Mohr circle, okay, so this angle is 2 phi, right? And if you see your stress tensor, so in this stress tensor, let's say it has been expressed in some coordinate system. On this, only the sigma 1 2 and sigma 2 1 are active, others are 0, right? So this implies this represents this point here, right? Because um here only shear stress is present, tau 1 2, and normal stress is 0. Okay. So this point is represented by this matrix. It means you are at this coordinate system, and your principal values are aligned. So your 2 5 will now be equal to 90 degree. So your principal values are here. And you know that your maximum shearing direction is at 45-degree angle to the principal plane. It means you should move 90 degree here in the Mohr circle. If you move 90 degree, okay, from the principal direction, so you will reach at this point again, right? Which is nothing but the E1 itself. I mean, even E2, E3, even E2 coordinate system, right? So this point is corresponding to either even direction or E2 direction. So this may be E2 and this may be even. So that's why your sharing stress, maximum sharing stress is aligned along even E2. Okay, so going to the next question. So the value of shear component of traction was you have to tell, and the options are A, radius of Mohr circle, B, the center of Mohr circle, and C, diameter of Mohr circle. And D, none of these. So obviously the answer will be this one, radius of Mohr circle, because from the radius of the Mohr circle only you will get the value of shear component of traction. So the next question says, the point on sigma axis where Mohr circle touches the touches touching it. This point on sigma axis where Mohr circle touches the sigma axis. What does it denote? First option is, does it denote principal stress components? Second option is, does it denote maximum shear traction? Or does it denote octahedral stress or fourth? Okay. So the point on sigma axis where more circle touches it. So more circle touches the x-axis or touches the x-axis where your stress values are equal to principal stress components. So that's why option A will be correct. Let's go to question number 10. It says the following state of stress exists at a point that is given by sigma, which is 540, 430, and 008. Right. So you have to find the principal stresses. Those principal stresses are obviously do eigenvalue analysis. So if you do eigenvalue analysis, um, this is actually lambda 3, right? Because you see here that the traction vector acting on a plane with plane normal E3 only has normal component, shear components are zeros. That's why. So lambda 3, lambda 3 is already given to you. So you only need to solve this 2 cross 2 matrix for getting the other two eigenvalues. So if you do that, so you can do 5 minus lambda 4. I mean, this will be sigma minus lambda. You can just try. So determinant of sigma minus lambda. We do that. So you can just solve this 2 cross 2 matrix also. So if you can just write in 2 cross 2 here. So you do that, so you'll get 5 minus lambda 4, 4, 3 minus lambda. And if you take determinant of this to 0, so you'll get lambda square minus 8 lambda plus 8 minus 16. Because if you multiply these two equations, you'll get lambda square minus 5 lambda, sorry, minus 8 lambda plus 15 and then minus 16. If you solve this equation, so you finally will get lambda square minus 8 lambda minus 1, that is equal to 0. If you solve, you will get lambda 1 is equal to 4 plus root 17 and lambda 2 is equal to 4 minus root 17. And obviously lambda 3 is 8, right? So principal sizes you have found out. Now what you have to find next is because this was already a principal component. So in that case, you can reduce your stress tensor and then just find other two eigenvalues. Okay, so what are the magnitudes of normal and shear components of traction on a plane whose normal lies in xy plane and makes an angle of 45 degree clockwise. Okay. Obviously, you have to specify axis. So you have to tell me that what are the magnitudes of normal and shear components of traction on a plane whose normal lies in xy plane and makes an angle of 45 degrees clockwise from the x-axis. So you just have to apply the formula. So let me just do this. So let's say this is your x-axis, this is your y-axis. It's making 45-degree angle. It's normal. It's making 45-degree clockwise. But you know that from the x-axis we have to take angle anti-clockwise. So we can say that this is minus 45 degree. So let's say we take unit vector here because we have to take unit normal vector. So n will be given by first component will be cos of minus 45 degree. That will be along x-axis, and this will be sine of minus 45 degree, and third component will be 0 because it's line xy plane. Okay, so that will be nothing but that will be nothing but minus 1 by root 2 minus 1 by root 2 and 0. So T will be equal to sigma times n now. You have n, you have sigma, just find T. Okay, so T 540, 430, and 008, you just put here. So and this put as minus 1 by root 2. So we can just see here that this is 5 minus 5 by root 2 and minus 4 by root 2. I think just complete a mistake here. So cos of minus theta is cos theta only. So that's why this is cos 45 degrees. So 1 by root 2 minus 1 by root 2 will come. So if you multiply, you get 5 by root 2 minus 4 by root 2. So you'll get 1 by root 2 again. And here you will get 4 by root 2 minus 3 by root 2, which is 1 by root minus 1 by root 2. So 4 by root 2 minus 3 by root 2. So you get 1 by root 2 again here. Okay. This is the final traction vector that you are getting. Okay. Now you have to find the magnitude of normal component. So magnitude of normal component will be sigma and n, that will be given by T dot n. So we'll do T. So this is T, and you do dot product with n. N was you do it, so you'll get, what will you get? You get 0. Sigma n is 0. And so really you have to find shears. Magnitude of shears just so that will T squared. Sigma square will be T square minus sigma n square and n square. So T, magnitude of T actually, yeah. So magnitude of T is nothing but 1 by 2 plus 1 by 2, that is 1 minus 0, so you get 1 here. Okay, so tau square is 1 actually. Magnitude obviously magnitude of tau will be 1. That's how you will find magnitude of normal and shear components of traction on a plane whose normal is some information about normal is given to you. Now let's do the last problem. So last problem says you have to think of a thin plate in XY plane being pulled from its sides such that sigma xx is equal to sigma yy is equal to 5 and sigma zz is 0. And it's given to you that all the shear stresses, all the shear stress components are 0. Means it's a principal plane. Okay, so x and y directions are principal directions, and z also. So you have to say that which of the following um, which of the following hold true for its Mohr circle corresponding to plane normals which are perpendicular to x-axis. So point 8 says the Mohr circle passes through the origin and its radius is 0.5. Radius actually is equal to P is Mohr circle reduces to a point. P is Mohr circle passes through origin and radius equals to 5. And D is none of these. Okay. So you see here that there is a thin plate in xy plane being pulled from its sides such that sigma xx, sigma y is 5, sigma z is 0. All the shear stress components are 0. It means x, y, z are principal planes. Which of the following hold true for its Mohr circle corresponding to plane normals which are perpendicular to x-axis? Now plane normals are perpendicular to x-axis. It means, let's say this is your x, this is y, x, y, and this is your z. Now plane normals are perpendicular to x-axis. So um, you will move in YZ plane, right? So all your plane normals will be in YZ plane. So either it will be like this or it will be like this. So all those plane normals in YZ plane So you have to draw more circle in YZ plane. So in YZ plane, principal stresses are sigma YY is 5, sigma ZZ is 0. So more circle that you will get will be, so let's say this is Y, this is Z. I mean, sorry, yeah, this is normal stress, this is shear stress. In the, so this is in YZ plane. So here you will get sigma YY and here you get sigma ZZ, which is 0. The sigma YY, this is 5, right? The more circle that you will get will be something of like this. Okay. So obviously the radius now will be okay. Maybe first option should be does not passes. Does not pass too much. Okay, so you can see here that the Morse circle is not passing through origin and its radius is 2.5, right? This is 2.5, this is 2.5. So obviously the first option will be correct. Second option is more circle reduces to a point. It will only happen when you would have taken this perpendicular to z-axis. All the normals, if they are perpendicular to z-axis, so you'll be next. All the normals will be in xy plane. So now you will have all both the principal stresses at a particular point. So that will reduce to a point. So more circle passes through origin and radius is equal to 5. Radius cannot be equal to 5 because either you can have a combination of 5,5 or 5,0. If you have, so radius cannot be actually equal to 5. Diameter can be equal to 5. Okay, so option A is correct. So we'll stop here for today and we'll meet in the next week. Thank you for your attention.